Hi everyone, in this video we are going to review the water we drink module. So the way I do my reviews is I split them into two different sections. I have a context section and a chemistry section. My context section is primarily the memorization, the things you just need to memorize, whereas my chemistry section is more often my application. So things you need to learn and then you need to be able to apply these skills if you see a new problem. So we're going to start off with the context section, and then at the very end, after I talk about the chemistry, we have three problems to kind of review this, and I personally think they're some of our harder problems that you could see on the exam. Alright, number one, I start off by talking about the context, so my memorization section. Now, we started off by talking about water. Obviously, this is a water module. We talked a lot about water, this module. So now, we broke it into a lot of different sections. We talked about the water treatment. So we know the actual cycle, we know the process of how we actually clean our water. We also talked about our MCLGs and our MCLs, so our maximum containment levels and our maximum containment level goals. We also talked about two different laws that we put into act. So we have the Clean Water Act, which came first, primarily dealt with our surface water, and then after that we have our Safe Drinking Water Act. So that came very shortly after the Clean Water Act, about 2 years. Okay, and that's the one that we expanded to include groundwater. Now, after that, we talked about potable water, or water that is used for drinking or cooking. So one of the two. Now, when we talked about potable water, we were very clear that we had certain contaminants that we needed to be very careful with. Contaminants, there we go, struggling there. So we had certain contaminants that we had to be aware of, and so this kind of goes hand in hand with our MCL and our MCLGs, but we just have to make sure we're aware of it when we're drinking our water and cooking with our water. This is where we need to be our most cautious with our contaminants. And now I also wanted to put in here our dehydration symptoms, because we talked about dehydration and what can happen, how you can just be thirsty, or you could actually die if you don't have enough water. So there's a big range here, but we desperately need to be drinking a lot of water. Now, after this, we also talked about a couple of our main issues, and so I'm just going to globally say issues. And so one of the big thing we talked about was our water footprint. And so we realized how much water is needed to produce a cup of coffee or to produce a kilogram of chicken. I mean, it's something that we just have to think about. So instead of thinking about carbon footprints in this unit, we talked about water footprints. And now we also talked about our global water issues. Okay, so our global water issues were a lot of times talking about inefficiencies or contaminations. So they're big issues, but basically in that section we also reminded ourselves that here in the United States, our water is practically free and we are unbelievably spoiled, which is lucky and good for us, I guess. So alright, moving on, new section, we talked about our aqueous solutions. Now, when we talked about our aqueous solutions, we had a couple of different terms or pieces of information we need to know. The first thing is we talked about our solute, and I'm going to add in here that we talked about electrolytes again. We reminded ourselves what they were, and this reminded ourselves about how we use these ions when they're in our system, okay, to make our muscles contract and whatnot. Alright, now, we also talked about solutes and then our solvent, so the liquid component, and then we talked about our solution. Alright, so there's three different pieces. Solute, usually the solid, solvent, usually the liquid, solution, which is the solute that's put into the solvent, and the two of them together is your solution. Now, the last thing we talked about in terms of our context was our acids in nature. So this brought us full circle. We talked about two different modules from the previous semester, and we brought it all the way here now that we know what acids are, and actually talk about how we have unnatural acids that are existing currently in nature. Alright, that's it for the context. Now we moved on to the fun part, the chemistry section. And I'll tell you, this chemistry unit was really fun for me. I really enjoy talking about water. So now the first thing we did is we reviewed the water structure. So things that we learned over the last 9 months. First thing was we know that water has a bent structure with angles less than 109.5 degrees. Yes, you still need to know that information. We also reviewed that the molar mass of water is 18 grams per mole. Okay, it's about 1801, but 18 works just fine. We then reviewed our melting point and boiling point. We know that water melts at 0 degrees Celsius, and we know that it boils at 100 degrees Celsius. Yes, you need to know these. You absolutely need to know these. After that, we moved on and talked about polarity. So when we talked about polarity, we had three different categories. We had electronegativity, where we talked about how fluorine was more electronegative than oxygen, more electronegative than nitrogen, which is tied in third place with chlorine. We also talked about if you could have polar bonds. So polar bonds, polar covalent bonds or non-polar covalent bonds. There's a lot of different options. But then we talked about what happens when we bring our polar bonds together and create polar molecules, or how you can have polar molecules and polar bonds, but you could have a non-polar molecule with polar bonds. It just depends on the geometry. So that's our polarity section. After polarity, we moved on and we talked about intermolecular forces. Intermolecular forces. Now we talked about two different intermolecular forces, one significantly more than the other. So the first one we talked about was hydrogen bonding. We talked about this a lot, so you definitely need to know about hydrogen bonding. Two things I want to point out right here. The big things that hydrogen bonding is a result for is that ice floats. We also know that it has a very, very high specific heat capacity, and I'm actually going to add a third one here that I'm thinking about it, is that it has an incredibly high boiling point of 100 degrees Celsius. So hydrogen bonding is the reason why water is such a freak, and it's so unique, okay? But we need to know about hydrogen bonding as much as you possibly can. After that, we actually talked about ion dipole interactions. And so we did this in the context of solubility and talking about salt water and how our salt is dissolved into our water in our oceans. And we also talked about certain rules for solubility. So make sure you know those rules to help you predict when you're going to have a strong ion dipole interaction. Again, you only need to know the solubility rules for water, okay? For any other solvent, you absolutely will not need to know that. All right, so after we talked about this section, we moved on and we talked about ions. And so ions was a huge section in this module. So the first thing we did was very simply, we broke apart our cations and our anions, and we compared them to our polyatomic ions. So you need to make sure that if I give you a specific ion, you can identify, is it a cation, an anion, or a polyatomic ion? And realistically, you should be able to tell me if it's a polyatomic anion or a polyatomic cation. After that, we talked about what the definition is to have an ionic bond. We now know if you have an ionic bond, it's highly likely that you have an ionic compound. If you have an ionic compound, then it's highly likely that you have a very, very large lattice structure. Now, we talked about lattice structure, but we also took it a step further and we talked about the strengths of the lattice structure. So make sure you understand the strengths of the lattice structure and how to compare those. We have a problem like that at the end of this, so stick around if you have a question on that. All right, after ionic bonds, we moved on and we talked about ionic formulas. So you need to figure out, if you bring two ions together, what is going to be the ionic formula of the resulting ionic compound. You also need to know how to name the resulting ionic compound. What is the name of it? And so this is our nomenclature section. Luckily, the ionic compounds are really, really easy to name, so that wasn't too difficult, in my opinion. And then we moved on to concentration. And so the first thing we did is we reviewed old units that we'd known from a long, long time ago, which were ppm and ppb, but then we introduced this new unit, molarity, okay, which is our capital M. I would definitely make sure I know about molarity. Chemists use that all the time, absolutely. All right, after we talked about ions, we moved on to the very, very last section, which are acids and bases. Okay, acids and bases. So the first thing we did is we identified what makes something an acid or a base. So if we see H3O plus or H plus, automatically you know you're dealing with an acid. On the other side, if you see OH minus, you know absolutely you're talking about a base. Now, we took it a step further and we identified 3 strong acids and 3 strong bases that you absolutely need to memorize. So then we can compare our strong acids to our weak acids. Remember, our strong acids are the ones that fully dissociate, where our weak acids are the ones that stay partially intact. Partially intact could still just mean 99.9% dissociation, so keep that in your mind. All right, now the last thing we did in our acid-base section is we talked about pH, and we learned how to actually calculate pH, and we also learned how to calculate pH from OH and H plus concentration. So make sure you can do that from both species. The very, 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 very last thing we did in terms of the chemistry section is we discussed what neutralization reactions are. Neutralization reactions. And so just to review here, the big piece is you have to take a strong acid, so one of the 3 we memorize, treat it with a strong base, one of the 3 we memorize, and every single time you're going to create a salt and water. Every time. Sometimes you'll make it as an HOH instead of H2O, but just remember that's water. So hopefully that will help you guide you through this exam and actually understand what you need to do and how you actually put your neutralization reaction together. All right, that's it. That's all I have for the information in this unit. It's not too challenging, but there is a lot of it, and if you don't pay attention to details, you're really going to get tripped up. So now what I want to do is work through 3 of our more challenging problems that you could potentially see on an exam or a final exam. Number 1. This is kind of a long question, so just bear with me. If you want to zip forward, that's okay, I understand. Which molecule contains polar covalent bonds, but it is not a polar molecule? Okay, so which molecule contains polar covalent bonds but does not contain but is not a polar molecule? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's completely okay. The first thing you must do is actually draw out the molecule. So for chlorine, it's just diatomic chlorine. And I'm going to put my lone pairs in just for the sake of the argument. So right away what we can see is that I have two elements that are the exact same. So there is no way that that can be a polar bond. So chlorine cannot be an option. Next question, water. You draw out water. We know our structure. First thing we need to identify, does it have polar covalent bonds? Absolutely. Oxygen is significantly more electronegative than hydrogen. This is definitely a polar covalent bond. Now, the next question is, we're looking for something that is not a polar molecule. So we're looking for a non-polar molecule. Water is definitely polar. I can split it in half and have a negative side and a positive side. So is water a non-polar molecule? No, it can't be an option. So now, we already know that BCl has to be the answer, but let's just check it and make sure. So if you draw this out properly, you should get something like this. And then if you draw on your charges, we know that chlorine is significantly more electronegative than boron, and we just know that because it's the third most electronegative atom. So the first thing we can do is say, yes, that our chlorine is negative, boron's positive, we definitely have polar bonds, so that's good. But now we're looking for a non-polar molecule, and there is definitely no way at all whatsoever that I can draw a line to split that molecule up to have a positive side and a negative side. So even though BCl has polar bonds, it is a non-polar molecule. So it has polar bonds, but it's a non-polar molecule. So the answer is definitely BCl3. Hopefully that made sense. If it didn't, stop, shoot me an email, or talk to your teacher about it. All right, next question. Which molecule has the strongest lattice? So we're talking about ionic compounds. Which one has the strongest lattice? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. Don't worry about it. We'll work through this together. So if we're looking for a strong lattice, right away we're looking for big charges and small species, okay? Big charges, small species. So the first thing we're going to go through is identify our charges. Potassium's going to be a +1, chlorine's going to be a -1. Calcium's +2, chlorine is -1. Barium is also +2, chlorine is -1. So right away I can look over here and say that my KCl has the lower charges or weaker charges than my other two components. So KCl is immediately out of the running. All right, so now we can look at calcium chloride and barium chloride. What we need to do now is figure out which one is going to be the strongest. And just remember your trend, okay? Your biggest atoms are going to be in this bottom corner. So these are going to be your biggest. And one in the top right corner are going to be your smallest. And so all we need to do is compare calcium and barium. And what we can see here in group 2 is that calcium is much, much smaller than barium. So right away we want to eliminate our big ion, so eliminate barium, and the only thing left would be calcium chloride. So always remember, charge is the most important thing. After charge, then we go to radii or radius. And we just can use this global trend of saying our biggest ones are down in the corner. Remember, francium is fat. Okay, that's your biggest one. She's in the bottom left corner. All right, last question, and this one is long. You're going to have to do some math about it, so don't get frustrated, but work through this because this is absolutely a fair exam question. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. This one is definitely more challenging. It takes a while to get this answer. So let's start off from the very beginning. If you see your strong base, right away you know that KOH always breaks apart into K plus and OH minus every single time. It's a strong base. So what that means is you can ignore your potassium ion. All you have to do is focus on your OH. So now what we need to do is just determine our OH minus concentration from the information provided to us in the problem. So the first thing I see is that I have 1.2 grams of KOH in 1,250 milliliters of water. Now that's in milliliters, so right away you should be thinking, red flag, that's bad. You need this to be in liters, so you just divide by 1,000 and you end up with 1.250 liters of water. So if you solve this out, you end up with something like 0.96 grams per liter for your hydroxide concentration. But grams per liter is a useless unit. That doesn't help us at all. So what we need to do is get it into molarity, or moles per liter. So we're just going to use the same number, 0.96 grams. Of course, this is of KOH, and this is per every 1 liter of solution, basically. So now what we're going to do is convert from grams to moles. So all you have to do is use your periodic table. Determine the molar mass of potassium hydroxide, and if you do that properly, you should get something like 56.11 grams of KOH. And that's for every 1 mole of KOH. So now check your units, your grams cancel out, and you're left with moles per liter, a beautiful molarity unit. And so if you do this properly, you get the answer of 0.0171 molar. This is equal to your hydroxide concentration. Now we're ready to get started. Now we just have to use 2 different equations. So now we have H plus, we multiply that times OH minus, and we get our KW value, so 1 times 10 to the negative 14th. And now what we can do is just slip these values in and solve for our H plus concentration. So we're looking for our hydronium ion concentration. We know our OH minus concentration is 0.0171 molar, and that is equal to 1 times 10 to the negative 14th. Now, if you do this properly, you can solve for your hydronium ion concentration. So 1 times 10 to the negative 14th divided by 0.0171, and we get a value of 5.84 times 10 to the negative 13th molar. We're still not done. The question asks for our pH. We have one more step. The very, very last step is we have to use this equation. pH is equal to negative log of our H plus concentration. All you have to do is just plug in that value. So pH is equal to negative log of 5.84 times 10 to the negative 13 molar. And if you plug this all in properly, you end up with a pH value which is equal to 12.233, but we usually only report pH to 1 decimal point, so 12.2 is great. Did you get it? Hopefully you did. It was a long problem, but it's a fair problem. Now you've seen this worked out, so make sure you can do this if you see something similar to that on the exam. Good luck, take care of yourself, and for the last time ever, drink, and drink your water. Have a great week, guys.